Hello and welcome back, statisticians. We're heading on into section 6.4. We've been talking about normal curves and normal distributions, and now we're actually going to look at some of the applications of the normal distribution. Things that we're going to be covering in this little lesson is finding the probabilities for normally distributed variables by converting them to standard normal variables. In other words, going back and forth using the formula to convert from data values to z values and z values to data values. Data values being your x, and we're also going to look at sets of data to see if they are normally distributed. So we're going to be checking for normal distribution. So let's get rolling. When we look at this normal distribution here, here's a distribution for the commute times for XYZ employees. This is the normal curve, and 4 is your standard deviation. So if you remember in class, we did an Excel activity where we actually put our data on the normal curve to check if it was bell-shaped to see if it was normal. If you understood that, you'll get this as well. It says that the mean of the morning commute is 18 minutes. That goes right there in the middle where the 0 would be on the standard normal curve, and the standard deviation was 4 minutes. So you're going to be going out 4 minutes in order to fill these values in these boxes down here. You're going to sketch the normal curve showing the commute times at 1, 2, 3 standard deviations from the mean. So if this is 18, that's the mean. We're going to add 1 standard deviation to it. Standard deviation is 4 minutes. So 18 plus 4 would give us 22 minutes. To keep going forward, we'll just keep adding 4. So to get the next group of data to go 2 standard deviations, we'll add another 4 to it to get 26. And to get 3 standard deviations, we'll get 30. To go to the left side, we're going to be subtracting because these are negatives. We're minusing 1 standard deviation from the mean. So 18 minus 4 is 14, and minus 4 is 10, and minus 4 is 6. And you put them right there on the grid. So you can go back and forth from the standard normal curve to just using your own data to look where like 68% of the people. The reason you might want to do this is because you might want to say, well, how many employees have between 14 minutes and 22 minutes commute? 68% of them are going to fall in between here. And so you can do some things like that. All right, to solve application problems by using standard normal distribution, transform the original variable into a standard normal distribution by using the formula, the data value minus the mean over the standard deviation, which we've seen before. That's x minus mu over little sigma. Sigmita. I could do sigmita. When one must find the value of x, you can solve for x. If you know your algebra, multiply both sides by the standard deviation, that's z times the standard deviation, and then add on the mean. And so that isolates your x value. So you can go back and forth between the z value and your data value. A lot of students have trouble knowing whether they're finding a z value or whether they're going to find an x value. When are they doing what? So let's go forward to do some examples. Steps for finding probabilities for normally distributed variables may be found by converting them to a standard normal variable. First step is to sketch your situation. Convert value to a z-score using the formula, and use the chart or calculator to find the probability. So you're doing this in order to find the probability. So they might say, what's the probability that 68% of the people commute blah, blah, blah? And you're going back and forth there. This chart is on the back of your notes. So if you have your pre-printed notes here, the very last page, I put a chart because I thought it would break down when you're doing what. So you might even want to tear that off and look at it while we're going through this. Okay, let me show you how to use this procedure table. The first thing you need to answer is, what do I want to find? Do I want to find probability or a data value? And you determine this by the wording of the problem. If they give you the probability, like 1 out of 5 people surveyed, or the percentage of people who do such and such is blah, 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 then you're looking for a data value, because in the wording of the problem, they tell you what the probability is. On the other hand, they might ask you to find a probability. What's the probability that people have an 18 to 22 minute commute? They give you the data values. and you have to find the probability. So I'm going to do the left-hand side of your chart first to show you how this works. So what do you want to find? If I'm looking for a probability, I have to say, am I using technology or a table? You can use your graphing calculator or the table. And our table in our book is table E. You're going to have to convert the standard normal distribution to a z-score by using the data value minus the mean over the standard deviation, which we haven't done a lot before, but it's very simple. It's just a plug and chug process. And then you can look up the z-score in that table, which you've practiced, to find the corresponding area. And remember, the area is your probability. Using the graphing calculator, you got to use the technology, and we can do that in class. I'll help you with that in class. Now, on the other side of your table, it said identify the area between mu and x. So if I'm looking for a value of x, I have to identify the area. That's the probability that they gave you in the wording of the problem. And what you're going to do is look up the area in that table, and then you're going to have to solve for x using the x equal mu plus z times the standard deviation. That's when you use that formula that we had above there. All right, clear as mud. It will get easier as you practice, but I do think this flowchart will help you solve those problems. And don't you want to know how it really works? So you've got your chart there. Let's do an example, and I'll show you how this goes. And it's not that hard. You just have to kind of practice a couple times. It says the mean number of hours an American worker spends on the computer is 3.1. Assume the standard deviation is 0.5. Find the percentage, that's important, of workers who spend less than 3.5 hours per day on the computer. Assume the variable is normally distributed. That is very important. Since it's normally distributed, we can make a prediction. We want to know what percent spends 3.5 or less on the computer. So we're looking, when we draw our picture, the first step is to draw a picture. We're going to have 3.5 or less. Now I put it over on this side because it's larger than the mean. When you look at your little chart, you have to answer the first question. What are you looking for? Am I looking for probability or a data value? Since I am finding percentage, that should clue you in. You're looking for the probability. That's easy peasy. I need the area under the curve for x value less than 3.5. So this is what I'm trying to find. In order to do that, I need to convert this to a z-score. So I can use my table. So z equals the data value, which is 3.5, minus the mean, which is 3.1, over 0.5 standard deviation. So when I plug and chug that, I end up with 0.8. Looking it up on the table, it'll give me the area between 0, remember, and that data value. So the z-score is 0.8. The probability z's between these two is 0.2881. And because you're professionals, you know that to the left of 0, to the left of the mean, is half your data because it's normally distributed. So I just add 0.5 on there, and we get 0.7881. That's it. So 78% of the workers, or 79 if you round, spend less than 3.5 hours on the computer, which I bet it's more now because, boy, are we getting technologically savvy. Let's take a look at another one. Each month, an American household generates an average of 28 pounds of newspaper for garbage or recycling. Assume that the standard deviation is 2 pounds and assume the variable is approximately normally distributed. If a household is selected at random, find the probability of its generating between 27 and 31 pounds per month. What was the average? 28. 27 is to the left of that, 31 is to the right of that. So when we sketch our figure, we'll have the mean down the middle, the lower and the upper. So 27's to the left, 31's to the right. To find the area under that curve, we need to convert to the z-scores and add them. Because you are very professional, you know you can find the area on this side, and add it together. But first, let's get the z. So we use our formula for z, x1 minus the mean over little siggy. And so we'll have 27 minus 28 over 2. You get negative 0.5. Then find Z2, 31 minus 28. So we're using this data value minus the mean over the standard deviation gives us 1.5. There's our two Z values. Find the probability on your table, and you will find that they are 0.1915 and 0.04332. I'm sorry, that should be 0.4332. That is a typo. I apologize. So when you add those two together, you would get 0.6247. That's 62.47%. So the probability randomly selected household generates between 27 and 31 pounds of newspaper per month is 62.47. So you can see how important this is to statistics, this whole chapter. Then they ask you to find the probability that they generate more than 30.2 pounds per month. So draw the figure. 30.2 is to the right of the mean, so you're finding a tail. It's just like you did before with the finding the probabilities with the z-scores. It's just you have one extra step, and that is converting this data value to a z-score. So we're going to do z equals plug and chug into the formula. You'll get 1.1 equals z. You know that's the area between 0 and 1.1. So you'll subtract it from 0.5. And you'll get 0.1357, which is 13.5% approximately. So probability that a randomly selected household will generate more than 30.2 pounds of newspaper per month is 13.57. Bada boom, bada bing. Next example. The American Automobile Association reports that the average time it takes to respond to an emergency call is 25 minutes. Assume the variable is normally distributed. Standard deviation is 4.5. If 80 calls are randomly selected, approximately how many will be responded to in less than 15 minutes? This one looks a little different, doesn't it? Because it says 80 calls. But if you recall, probability, it's a percentage. So we're actually going to find the probability and take the percentage times the 80 calls. So if we do this less than 15 minutes, what was the mean? 25 minutes is the mean. It's to the left of the mean. So 15 would be drawn down here. 15 on down. So you're looking for a little tail. 15 minus 25 over 4.5. Negative 2.2 gives you your z-score. It's to the left of that. So the probability from 0 to negative 2.2 is 0.4868. That's from our table. So we got to subtract that from 0.5. So it's going to be 1.32%. Not very many, is it? So if 80 calls are selected at random, here's our percent. 1.32% of 80. So all you do is you multiply those two together, and you end up with 1.05. So approximately one call would be responded to in less than 15 minutes. That's a real shame. You would hope that it would, that's why you might want to be able to protect yourself. All right, normal distribution can also be used to find specific data values for given percentages. This application is shown in the next example. So all of those were examples where you were finding the probability. You were doing the left-hand side of the chart. Now we're going to look at the right-hand side of the chart, and we're going to find those data values. So here's our first problem where we're doing the other side of the chart. To qualify for a police academy, candidates must score in the top 10% on a general abilities test. The test has a mean of 200 and a standard deviation of 20. Find the lowest possible score to qualify. Assume the test scores are normally distributed. This is one of those, you see how they give you this percent? That is probability. That is an area under the curve. And so when we look at this, we're going to sketch the problem. Here's our normal curve. If it's the top 10%, that means it's this little tail over here, and they want to know the data value. I'm hoping you can get that in your head. This is a percent, so we're looking for a data value. They gave us the probability. So if you recall, here's the area under the curve. They're saying this part is 0.1, and we're looking for the data value. Mean is 200, so you're going to use that backwards formula. And our table gives us this white portion between the mean and this guy. So if this is 0.1, what's this white portion under the curve? Well, you get that by just subtracting from 0.5. So 0.5 minus 0.1, we're working backwards. So that area, the white portion under here, is 0.4. And that's what we're going to have to use to find our z-score. So we need our z-score to plug it in the formula. So when we look under our table, the area that corresponds to 0.4 isn't exactly right. So we're going to use 0.3997. That's close enough. If you go to the left and look above on that table, you will get 1.28. The area falls exactly halfway between two z values. Use the larger of the two. That's the tip for the day. So the corresponding z value in our case is 1.28. So this is 1.28, and we can find it. We have everything we need to find that x value. So substituting into the formula, we'll put the 1.28 in for z, and our standard deviation of 20, and our mean of 200. So when we do that out, we get 226. So you got to score 226 on that test in order to score in the upper 10%. All right. All right, so that's what it is. Now, that's how you find the data value. What clues you in you're looking for the data value and having to go through this working backwards procedure is that you're given the percent in the problem. So now we're going to move along and talk about determining normality. It's because many of these distributions are supposed to be normal, we need to check it. The easiest way is to draw a histogram and check its shape. If the histogram is not bell-shaped, then the data are not normally distributed. You can also check for its skewness by using Pearson's index of skewness, the PI of skewness. And that's, I got a formula. It's 3 times your mean minus your median over your standard deviation. So that's what it is. If the index is greater than or equal to +1 or less than or equal to -1, it can be concluded that the data is significantly skewed. Data should also be checked for outliers. So in other words, if your PI is between -1 and 1, you're A-OK. Alrighty, if it's outside of that range, it is skewed, really skewed. So let's talk about this one. Example. You've got 18 high technology firms showed the number of days the inventory, blah, blah, blah. Here's your data. We're going to make our frequency distribution and use a class width of 25. At this point, they'll tell you what it is. So you might want to just let me go ahead and click through these and then pause it and write it down. But you start with your lowest one, which I put these in order for you. So 5 to 29. Remember that when you're doing class width, to go across, you're 1 less, so a 5 plus 24 to get the 29. But when you go down, you add 25 to it. So this would be 30 to 54, 55 to 79, and so on. Boundaries, go down a half a step, up a half a step from your class limits. So it's going to be 4.5 and 29.5. And you can just add 25 to that as you go down. Then the frequency is you check your data values and you count how many are between these two class boundaries. So pretend like you did that. There's 2, 3, 4, and so on. Looking at this, it looks pretty good because you notice it gets higher in the middle and it's lower on the ends. So when we go ahead and draw our histogram, here's your frequency, your days of inventory. You put these boundaries along the bottom. So between 4.5 and 29.5, you had, what was it, 2 or whatever. And so you draw your bar chart in there, and of course Excel does this for you. That's why Excel is a nice tool. If you look at this, it looks approximately bell-shaped. It's high in the middle and low on the ends. Ohio. No, that's a joke, isn't it? What's high in the middle and round on both ends? Ohio? I don't know. Anyhow, so if you look at this, it's approximately bell-shaped. Okay, so now we're going to check for skewness. So if we look, we're going to check for our skew, and we're going to use the PI, the Pearson's index of skewness. So all we have to do is plug and chug in that formula. 3 times the mean minus the median divided by the standard deviation. We plug that all in. Bada boom, bada bing. It kicks out 0.148. That is between -1 and 1, so it's not skewed. So pi is between -1 and 1. It's not significantly skewed. Next, let's check for outliers. If you remember, we need the interquartile range, quartile 1 and quartile 3. Quartile 1 is the median between the low data value and the median. So it's halfway in between the low value and the median, and the quartile 3 is halfway between the median and the upper high value. In this case, when you look at our data, take my word for it, quartile 1 is 45, quartile 3 is 98. So the interquartile range is the difference of those. So we subtract them and we get 53. Outlier would be 45 minus 1.5 times 53, or negative 34.5, or we add plus 1.5 times the interquartile range to get 177.5. So since none of our data lie outside of this range, we know we have no outliers. So there's no outliers in this case. All right, that's really all you need to know from section 6.4, and I will see you later.